stuff, but we have a couple of things we need to tidy up in terms of the integers. The first thing we want to check is that the integers are closed under z multiplication. So that is for any m and n an element of z, mn is an element of z. Okay, so we know the integers are closed under addition, and this is sort of the last thing we need to check as far as basic operations are concerned. So what we need to do, remember the situation here is that we have the real numbers, and we defined the natural numbers in a section that we didn't really cover, although I may go back and talk about it later if we have time. And then we defined the integers using the natural numbers, right? We just threw in 0 and we threw in all the negatives of natural numbers, and that got us the integers. And the integers then were closed under addition. That was something that was proved in that optional section as well. And so now we have this remaining thing. When you take an algebra course later, this is something you have to prove. So in the language of algebra, we're proving that z is a subgroup of the integers. Actually, we're proving it's a subring because, of R, because both addition and multiplication are closed. So these are the kind of proof we're doing now is the sort of thing you may do later in an algebra class, which is why I want to cover this thing. And this is now being proved by induction. Or at least the basic case, which is the integers. Okay, so we're going to start with m and n, an element of the natural numbers. And, you know, you can work too hard on this. Some of you sometimes work too hard on your homework to do things that are more complicated than necessary. You could try some kind of double induction in m and n, but you really don't have to do that in this case. What we're going to do is we're just going to use a fixed m, and we're going to do induction in n. Okay, so we're going to fix m, and then do induction in n. So what would be the base case? All right, we've got two things. We've got our base case, and then we've got the inductive step. So what's our base case going to be if we're doing induction in n, and we're doing this for all natural numbers, we're not starting anywhere else. What's the base case going to be? Yeah, base case will be n equal 1. Okay, so m times n equals m times 1 equals m, and actually we're assuming they're both in the natural numbers. We don't quite have to do that, but at any rate is an element of the natural numbers. So we're good, right? So what's going to be my opening line for the inductive step? What do I suppose? Yeah, so actually if you want to get as part of this that the natural numbers are closed, we can actually prove something slightly stronger here. So let's suppose this is an element of n, because we're actually getting both m and m in n there. What do I need to prove? Is a natural number, right? Because my statement is that if m and n are in the natural numbers, then m times n is a natural number. So we just start m times n plus 1, right? This is the thing we need to check. And so what am I going to do? Distribute. And now what? Right, so the inductive hypothesis, exactly, tells us, right, because this is in the natural numbers, mn is an element of the natural numbers, and n is given as a natural number. So this is a natural number by what property? Yeah, we know n is closed under addition. Okay, so let me point out why induction is useful here. I mean, you might think, okay, the natural numbers are closed under addition. Why? Because addition is just a bunch of multiplications, right, when it comes to the natural numbers, right? I mean, 5 times 3 is 5 plus 5 plus 5, or 3 plus 3 plus 3 plus 3 plus 3. So therefore it follows, okay? This is a fairly simple case, but that's sort of a matter of hand waving, and it actually probably takes more breath to talk about it and more space to write something like that down than to just go directly to induction and nail it very clearly. Okay, so even in a simple case like this, the induction lets you really get a proof with no hand waving, right? So you probably by now have heard of hand waving arguments, right? And that's what we're not really allowed to do in this class. We've got to nail everything down. Okay, so we're okay with natural numbers. Okay, now let's suppose, so basically we're just going to go through cases and try to be as efficient as possible. Suppose m equals 0. Then what is mn? Yeah, equals 0, which is an element of the integers, right? Okay, so then n equals 0, similar. And then we've got some other possibilities. So let's suppose that m less than 0 and n less than 0.
Mn is greater than 0. So
yeah, but we want to use the case that we already did before. So we need a kind of initial step here, right? I mean, the right idea, you want to negate stuff, but
that means negative m and negative n are natural numbers.
yeah, negative m and minus n are natural numbers, right? I mean, right? I mean, the minus sign makes them positive, okay? So as weird as that looks, I mean, this is true, right? Okay? And now, what do we do? Well, so by the above case, so let's just start from the beginning. Again, your goal in here, whenever possible, should be to write things out linearly and not do sort of parallel things, right? So let's just start from the beginning. Mn equals minus m. Oh, let's just do it this way. Minus m times minus n, that's just field axioms, right? Sorry, what am I saying here, right? An element of z. I'm going in circles, right? This is almost too, okay. Right? Actually, it's an element of n, we'll put it that way. Okay, and then the other cases are similar, right? Just by inserting. So other cases are similar, right? Whenever you have something negative, you can just negate it to make it positive, and then you can apply the previous case and sort through your minus signs, which is probably the hardest part of the proof. Okay, so the integers are now closed under multiplication. So this actually is necessary for a lot of the stuff that James did before, right? Because you want to make sure that when you multiply two integers, you actually have an integer back. Okay, but we've nailed that. Questions about this particular operation? Multiplication. All right, let's discuss now powers by integers. Now again, we have to define these things, right? So for example, let's suppose we wanted to define a to the fifth. Well, to define a to the fifth, we could say, well, that's just a times a times a times a times a. 5 times, okay? Well, what's a to the 107? You know what it is. You can say it. Well, that's just a multiplied by itself 107 times. But that's not going to be useful in a proof of anything, right? This is kind of like what we did over here, where multiplication is repeated addition, powers are repeated multiplication, and so you ought to be thinking at this point that we ought to somehow try to use induction for this, right? Especially if we're going to try to prove things about it. And so what we're going to do is, first of all, we're going to define, so this is, for starters, we'll just say A an element of R. We're going to define A to the 1, well, what should that be? That should just be A, right? And then for any n, we're going to define A to the n plus 1 equal A to the n times A. Okay, now you say, well, we didn't really define it, right? Didn't really kind of define anything, but let's check that, right? Because we have induction. And so let's consider the statement that we have defined A to the n for all n. Is this a true statement? Well, we'll do it by induction. Have we defined A to the 1? Yes. Okay, so the base case is correct. The next statement is, well, if we have defined it for A to the n, have we then defined it for A to the n plus 1? And the answer is yes, we just did it right there. Okay, so by induction, we have defined A to the n for all n. Now this kind of definition has a special name. Okay, some people refer to it as an inductive definition, but more often it's called an iterative definition. And these come up a lot in mathematics because sometimes you want to define something for all n, and we'll see a little of that later, right? And so basically, to do an iterative definition, you have a base case. In this case, it's 1. And then you suppose you have defined it for the nth case, and then you say how to get the n plus first case out of it. And that can be more or less, usually more complicated, right? It's hard to get less complicated than this, so it's generally more complicated. Does everybody understand that we've now defined this for all n? And having defined it this way, this is how we have to use it in our proofs, right? If we're going to prove something about this, like the powers rule, which is what we're going to do next, then we have to use our definition, right? So we're going to show the powers rule now. Again, we're going to have to go through cases. It'll be a little bit tedious, and again, part of the point is to try to make the cases as efficient as possible so you can do the least amount of work, right? The idea is to be lazy, right? And only do what's, the minimum that's necessary to get a correct answer. Okay, so we're going to check powers rule. A to the m, A to the n equals A to the m plus n. And for starters, we're going to say m and n are natural numbers, and then we'll extend this to a statement about the integers. Well, thinking about what we did before, what would be a reasonable strategy here? Thinking about how we proved this over there. Induction, and more specifically, yeah, let's just fix m. Okay, again, we'll fix m. Since it's arbitrary, then this will be true for all m, right? As long there's no special properties of m that I'm using except that it's a natural number. And induction on n. Exactly. Okay, and so let's look at the base case. The base case is going to be what? A to the m times A to the 1, right? And we want to show that's A to the m plus 1. Okay, but by definition, what is A to the 1? And I'm being very careful here, right? Not to skip anything, because we're proving this. Right? And this is another one of the sort of discipline exercises, right? Everything you do, it's all so familiar, right? That it's easy to skip over something. In your homework, you may be tempted to skip something, all right? So just be careful. So this is, by definition, A to the 1 is A. And now what?
precisely the definition of a to the m plus 1.
Yeah, this is again definition a to the m plus 1. Right? That's our iterative definition in action. And it's not a coincidence that we used the base case of the definition to prove the base case of this case, and the inductive part of the definition to prove, well, we used it right actually there, okay? And so then the inductive step, what do we suppose in this case?
That a to the m is a to the m.
Yeah, so we suppose again that the P of n statement is true. Okay, so what is this? This is going to be a to the m, a to the n equals a to the m plus n. And we want to consider a to the m times a to the n plus 1.